Hello my dear students, welcome back to NEET WORLD. So today we will be discussing the SAQ questions of IPE first year syllabus. Okay, so now here if you observe, this is our C60 material. So this material is highly helpful for your IPE preparation, whether you might be first year or second year. So for both first year and second year students, you can access this material. So you can access this material for free of cost from our side. So this is like from the NEET WORLD side, we will be providing free study materials for all the first year and second year IPE students, for all science subject students, like whether it may be mathematics, physics, chemistry and also biology for BPC students. Okay, so now you can access all this materials like C60. See, there is no proper material in the market right now. So by looking at that gap, so we have prepared this C60 material. So this C60 material contains all the important questions that must be focused to get 60 out of 60 in your chemistry subject, whether it might be first year or second year for both Andhra Pradesh and Telangana state students. Okay, so now how can you access this material? See, just go to Play Store and download MedWorld app. What I am saying, just download MedWorld app. Okay, so after downloading this MedWorld app, so just in the chat box, just log in it. So just say hi in the chat box, just say hi in the chat box. So our team will share you this modules. Okay, so these booklets, whatever it is required for your IPE preparation for Telangana and AP students, so our team will share this access like complete modules for if you are MPC. So these 3 books will be provided. If you are BPC, these 3 books will be provided. Okay, so hope everything is clear. So now this book includes everything like LAQs, SAQs, very short answer type questions. Okay, and chapter wise weightage. Okay, and for practice purpose you will be having like model papers and also previous year papers. And you know guys, one more thing, for each and every answer clear explanation is written and that will be provided in that PDFs. Okay, so this is not just a question paper list, not a list of questions, but it is a list of questions plus answers with a clear explanation. And you know guys, one more thing, so now once after downloading this, now you can come to this NEET WORLD NEET WORLD YouTube channel itself. So if you observe in our live sessions, every day we are taking one live session for each subject. It means that is for IPE students. Okay, so one live for first year students and one live for second year students for chemistry subject, as well as physics, as well as mathematics, as well as biology. Okay, right. So now you just download this and attend this free live sessions on our NEET WORLD YouTube channel. Okay, so by making this both things, you can make your preparation more effective. Like you know, every answer that is provided in these modules will be clearly explained in these free live sessions. Okay, I hope you are following these sessions regularly. If not, just follow this from now onwards, and you can also share with your friends so that your preparation will be more easier and it will be more productive. Okay, because most of the students are worried about learning the answer, like they will be looking for someone to help them in understanding that particular question for answer for each of the question right now. So here we are to make that to make your preparation more smoother and also more easier to gain maximum marks. So just join our free live sessions using these modules. That's it. Okay, I hope whatever we discussed here is clear. Now let us start our discussion on the SAQ part of first year IPE. Okay, so in the last session, if you observe, these are the chapters we have from first year syllabus, right? So from this chapter, in the last live sessions, I have covered structure of atom, 2 questions from structure of atom, that Bohr model and quantum numbers. Okay, and the next classification of elements are also completed. Okay, there are 3 questions we have completed. What are the 3 questions from classification of elements? Periodicity in properties like atomic radius, ionization energy, electronegativity, electron affinity, these things. Yes, this is over. The next comparison of IE1 and IE2 is also discussed. Then next like explanation or classification of SPDF shells, I mean blocks in the periodic table. Okay, like classification of blocks in the periodic table. Okay, that's it. Next one is organic chemistry is also clearly discussed right now. So the next, so from this 1 to 4, these are the 4 chapters. These are the 1 to 4. So these are the 3 chapters you can expect LAQs. Okay, and there are some chances to ask LAQ question from this chemical bonding also. Okay, so now what we need to do, so if this chemical bonding LAQ question is not appear, then the same question may appears here as a 4 marks in your SAQs. Okay, so chemical bonding may also asked in 4 marks. If not in 8 marks, it will be appears in 4 marks. So we need to study chemical bonding also. Okay, now in this session I will be explaining 4 marks LAQ questions first. After that the first SAQ questions first for this chemical bonding. Okay, and after that we will be looking into some important questions like that will be possibly asked in this LAQs for this chemical bonding. Okay, let me give you the list of that questions first. See here you have, these are the short answer type questions from chemical bonding. That means 4 marks question from chemical bonding. These are 4 marks questions from chemical bonding. So just guys listen to me till the session, till the end of this session, so that you will get complete clarity on our discussion. Look at this, what I am saying, Fazan's rule states, look at this, state Fazan's rule with a suitable example. Okay, so it is again very important for your EAP set NEET also, like NEET JE also, but anyways listen to me, I will be explaining this for 4 marks. Okay, as per your IPE exam syllabus. Okay, so just look at here what it says, state Fazan's rule and explain with suitable example. Okay, give suitable examples. See here what exactly Fazan's rule here is. It explains, I will be saying orally first, then you can go through these points. Okay, it explains the covalent nature in ionic compounds. Okay, so there are some ionic compounds and there are some covalent compounds right now. So there is no 100% ionic, there is no 100% covalent compound. Okay, so every ionic compound have some minimum amount of covalent nature. For example, we are saying NaCl, what we are saying, NaCl is an ionic compound, right? So it is not 100% ionic. What I am saying, this is not 100% ionic. Okay, so it means there is some percentage of covalent nature also. Okay, what I am saying, it is an ionic compound but not purely ionic. Okay, so every ionic compound contains some percentage of covalent character. This is what you need to know first. Okay, so now how much what is the quantity, or I can say how can we relate or how can we compare the covalent nature of this ionic compounds is explained by this Fazan's rule. Okay, so that is explained by this Fazan's rule. So what it says, these rules explain when an ionic compound acquires covalent character. So what is the use of Fazan's rules? Fazan's rule explains covalent nature of ionic compounds. That's it. Fazan's rules explains covalent nature of ionic compounds. This is the first line you need to mention. Okay, and after that, so now what are the factors deciding covalent nature in the ionic compounds? Okay, so what are the factors deciding covalent nature in the ionic compounds? For example, whatever the ionic compound we are taking here, let us say NaCl only we will see here. So I am writing NaCl, it means we have one cation Na plus and one anion right now. So in ionic compounds there will be cationic part, anionic part, we know this. Okay, so now for this particular ionic compound, how much amount how much covalent character is there, that will depends on 4 factors, like 5 factors. What are those 5 factors? So first one is with respect to anion, if I talk, with respect to anion and with respect to cation we should mention. Okay, first one with respect to cation I am saying, first one is with respect to cation. So cation should be smaller size, what I am saying, cation should be small size. Okay, so effect of size of cation, small size cation. Okay, you should just remember like this, cation size should be small. Okay, small size cation, cation should be small size. Okay, and cation should have more positive charge. What I am writing, more positive charge, then that compound will results to have more covalent nature. Okay, for an ionic compound, its covalent nature depends on cation as well as anion. Okay, with respect to cation, if I say, so cation should be small size and it should have more positive charge. So if these two factors are there, then we can say that compound will be having, that ionic compound will be having more covalent nature. Okay, so for example, I will be mentioning one example. Just see here what I am saying. So here I am writing NaCl and MgCl2. Now what you are seeing here, Na means Na plus is a cation here, and here Mg plus 2 is a cation. So now what you are seeing here, see where do we have small size, see Mg plus 2 is small size now, from left to right what happens, from left to right what happens, size decreases now, so that's why magnesium will be, second group elements will be smaller than first group, that we know. But one more thing here, it is having one positive charge, here it is having 2 plus 2 charge. It means where do we have more positive charge, where do we have more nuclear charge, here now. So that's why more small size, more positive charge, that makes this compound to be more covalent. Both of them are ionic, but out of that two ionic compounds, one is having more covalent nature and one is less covalent nature. That covalent character is decided by cation as well as anion. When I talk about cation, it should be small size and it should have more positive charge. So that's why MgCl2 is more covalent when we compare with NaCl. That's it. Okay, is this clear? So if I am saying this is more covalent, that will be less ionic, this will be more ionic, like that. Okay, right. This discussion is clear now. So effect of cation or factor of cation deciding whether it is covalent or ionic, is this clear or not? Yeah, so now in the same way we will be discussing about anion also. With respect to anion we will discuss now. So when you compare about anion, so anion should be large size, anion should be large size and it should have more negative charge. What it should have? More negative charge. Here cation should be small size, anion should be large size, remember. Okay, anion should be large size, cation should be small size, and cation should have more positive charge, anion should have more negative charge. So these resulting, these factors, these two factors, I mean these complete factors of anion and cation results to show more covalent nature. What that will result? It will results to more covalent nature. Okay, right. And look at here, I will be giving one more question here. Just see what I am saying. NaBr I have and NaCl I have. Which is more covalent, I am asking. Both of them are ionic first, but which is having more covalent nature or less ionic character between these two? This is what the comparison you need to do. Here if you observe, cation is having same, cation is same here, Na plus and Na plus, but here bromide ion, here it is chloride ion. So we know, so down the group chlorine, bromine, like this we have fluorine, chlorine, bromine, iodine, like this. So down the group what happens to size? Size increases now. So bromide ion is larger when compared with the chloride ion. So this will make large size anion now. So it means polarizability of that anion will be more, so that will make the compound to be more covalent. So the covalent nature of NaBr is greater than NaCl. That's it. Okay, so this explanation is clear now. Now read one by one these points whatever I have mentioned. Effect of anion size. So what is the effect of anion size? Larger anion, if the size of anion is larger, it will be having more covalent nature. That's it. So example, Br minus and I minus. If I compare, I minus will be greater size, so that will make lithium iodide is more covalent than lithium bromide. So what is the reason? Because anion size here, if you observe, anion iodide ion is larger size than bromide ion. That's why lithium iodide is more covalent than lithium bromide. That's it. Okay, is this clear? So guys, those who are clear with this, click on the like button guys. Yes, if this is clear, just click on the like button. Okay, then next, what is the effect of cation size? Just see here, what is the effect of cation if you observe? Smaller cation size should be small, so it will results to have more covalent character. Why? Because small cation, more positive charge, therefore it makes cation to have more polarizing power. Okay, it means that will attract the electron cloud of anion more effectively, so that results to covalent character. That's what. So cation smaller, so higher will be the covalent character for that compound. Okay, example here, lithium plus is small, forms more covalent compound than Na plus. It means if I say LiCl, NaCl, so which is more covalent here? See lithium, see anions are same here, so you cannot explain with respect to anion in this case. So look at the cation, this small size cation now, so positive charge is also same, but small size cation here lithium, so that makes it to be more covalent when we compare with the NaCl. That's it. This is the order of the compounds, covalent character order. Okay, now what is the effect of charge? Effective charge, whether it may be negative charge or positive charge, it should be high. Okay, higher the charge on cation or higher the charge on anion, stronger the attraction, more covalent character will be the compound. Okay, so compound will have more covalent character. That's it. Okay, example here, so Al plus forms more covalent compound than Na plus, because here more positive charge now, so that's why it is making it to be more covalent compound when we compare with the Na plus. Okay, right. Is this clear? Yes, I hope this is also clear. The next, electronic configuration. Yes, this is one more factor to be remembered. Okay, see, when we are writing electronic configuration for alkali metal, what you are saying, for example, sodium I am writing. Here sodium electronic configuration, how you are writing? It is atomic number 11. So you are writing here like 1s2, 2s2, 2s2, 2p, 2p6, 3s1, like this we are writing. Atomic number 11 means like this you are writing. So here you are following octet electronic configuration, I mean like 8 electrons are there in the octet, like that we are seeing right now. So but when it comes to the species like Na plus, means NaCl is there, CuCl is there. So in between this, which is more covalent character they will ask, which is having more covalent character they will ask. How do you decide? See, anions are same here, so you cannot give your answer with respect to anion because they are same. But here if you observe, cation is Na plus and here it is copper plus, Cu plus. So out of these two, which is more which results to have more covalent character? So that depends on their electronic configuration also. So here if you observe, cation with pseudo inert gas configuration favors more covalency. It means here if you observe, you are writing 18 electron rule, I mean 18 electrons in it. So because what is the element here you are taking? Here you are taking neon, this is 10, after that you are writing 3s1 electronic configuration. But for copper it is 29, copper is 29. It means what you are writing here? So argon, 18 are there, noble gas. Here you have 18 electronic configuration, here you just have 8 electronic configuration. After that you are writing 3d10, 4s1. Normally in atomic state, in ionic state it will be 0 here. Okay, like that we are making. So here 18 electrons are involving. Now this 18 electron involvement is called pseudo inert gas configuration. What is that? Pseudo inert gas configuration. Whenever you have 8 electronic configuration and 18 electronic configuration, then like 8 electron configuration is inert gas, this 18 means pseudo inert gas. Whenever you have like this configuration, the pseudo inert gas configuration species will make it to be more covalent. That's why CuCl is more covalent than NaCl. That's it. Okay, is this clear? Now tell me between these two, ZnCl2 and here I am writing CaCl2. Between these two, tell me which is more covalent, which is more ionic here. See, if they ask for covalent nature, yes, ZnCl2 is more covalent. If they ask for ionic, CaCl2 is more ionic. How do you say this? Because it has 18 electronic configuration, but here you have only 8 electronic configuration. That's why ZnCl2 will make it to be more covalent character here. Just remember it. Okay, right. And after this, is this clear? Yes, guys, if this is clear, just click on the like button again. Yeah. So after this we will be discussing few more questions. Then next, write the general properties of ionic compounds. What are the general properties of ionic compounds? Okay, so look at here. Ionic compounds are formed by transfer of electrons from metal to non-metal. See how ionic compounds are formed by transfer of electrons. For example, here you have sodium atom here you have, and chlorine atom here you have. So this is atomic number 17 for chlorine, and here it is 11 for sodium. So now we know the element that is before this sodium will be neon. Right now neon gas configuration is 10, electrons are 10. So electrons are 10, it has a noble gas, like fully filled electronic configuration. No? So how many electrons are extra here? One more electron is extra. So that's way alkali metals loses one electron and becomes unipositive, Na plus, and electron is lost from its atom. Okay, so now whatever the last last electron is there now, that will be taken by this chlorine atom and it will become chloride ion, Cl minus. Okay, so like this. So now what is happening here? Na plus and Cl minus. So opposite charges now, so they will make a compound like NaCl. Okay, now what you are seeing, a complete transfer of electron is taking place from the sodium to chlorine right now. So that is what a ionic compound is formed by complete transfer of electrons from metal to non-metal. See, sodium is a metal, chlorine is a non-metal. So ionic compounds are formed generally by combination of a metal and a non-metal. Okay, what I am saying, ionic compounds are formed from the combination of metal and non-metals. Okay, remember this. Okay, so look at here, what are their importance? Okay, what are the importance of this ionic compound? See, you need to write as it is, like ionic compounds are formed by transfer of electrons from metal to non-metal. Okay, the next, producing a cation from metal and anion from non-metal that held together by electrostatic force of attraction. So what is that? Electrostatic force of attraction, that is nothing but ionic bond. Okay, now what are the importance of this important properties of this ionic compounds? First of all, physical state. Look at here, ionic compounds are crystalline solids. What they are? Ionic compounds are crystalline solids. Okay, crystalline solids at room temperature. Okay, they have rigid lattice structure. See, we are mentioning it as crystalline solids now. Yes, you are much familiar with this. So you know that table sugar at your home will be using for cooking purpose now. In curries we will be adding. So how it will be having crystalline nature now, very rough if you touch it right now. So that is nothing but NaCl, which is ionic compound which has a crystalline solid form. Okay, right. The next, they have very rigid lattice structure. It means Na plus and Cl minus are arranged properly with a very close packing in it. Okay, next, melting and boiling point. So ionic compounds have very high melting and boiling points. So due to electrostatic interaction between them, they will be very close. So when they are very close, attractions are more now. So in order to separate them, in order to convert them from one physical state to another physical state, it requires more energy, more temperature is required. That's why they have very high melting points and very high boiling points. Okay, then next, due to the strong electrostatic force of attraction between oppositely charged ions. So what is the reason for this? This is due to high melting and boiling point is due to strong electrostatic force of attraction between oppositely charged ions like cation and anion. Okay, this is the reason. Okay, then next, solubility. Ionic compounds are soluble in polar solvents. What we are discussing? Ionic compounds are soluble in polar solvents like water, okay, and water, liquid ammonia, etc. So ionic compounds now, it will generate ions whenever we dissolve a ionic solid in the polar solvent. For example, NaCl only you take. So when it is dissolved in the, like when you kept in the water, it will dissociates like Na plus and Cl minus. So like this, all the water molecule will surround this cation and anion. So like this it will get dissolved. Okay, so ionic compounds will dissolve in polar solvents. What we are saying, polar solvent. Now what are the example of polar solvent? Best example is water. So that's why whenever you add salt to the water, what happens, it will properly dissolve. Okay, but ionic compounds does not dissolve in non-polar solvents. What we are saying, non-polar solvent, it won't dissolve. Okay, what are the examples here? Non-polar solvents like organic compounds like CCl4 or benzene, all this comes under the examples for non-polar solvents. Okay, so they are insoluble in non-polar solvents like benzene, ether, CCl4, like that. Okay, remember these 2 points are also important. It is about solubility property, that is ionic compounds property, that is third one, solubility. Okay, then next, reactivity. How do they react? So ionic compounds react very fast in aqueous solution. What they are saying, ionic compounds are react very fast. Ionic compounds are react very fast in aqueous solutions because ions are free to move and participate in the reactions. So ionic compounds are very fast because ions are freely moving here and there, so they will go and react with the other species. That's what ionic compounds are shows very fast reactions. Okay, right, because if you compare with covalent reactions, covalent compounds, see covalent compounds have bonds, no, so it will take time for breaking the bond and making the bonds in the covalent reactions, but in ionic compounds no such breaking and making the bonds, no, so they just get paired up with other ions. So it means ionic compounds are highly reactive or very fast reactive, means ionic compounds are shows very fast reaction in aqueous solutions because ionic compounds are free to move and participate in the chemical reaction. That's it. Okay, and the next, isomerism. Ionic compounds are non-directional. This one you need to mention. Ionic compounds are non-directional. Hence, ionic compounds do not show isomerism. Okay, so for isomerism there should be proper orientation. Okay, right. Here the next point is electrical conductivity. This is again important. So in solid state, what I am saying, in solid state ionic compounds does not conduct electricity, they are acting as a insulator. Okay, so in solid state they do not conduct electricity because ions are fixed in the lattice. See, if you take a crystal lattice like a sodium chloride crystal, if you take, it will be closely packed now like this. So here proper very close packing will be there, like Na plus Cl minus ions will be very closely packed. They are very rigid, they won't move here and there in their molten state. Therefore, if there is no movement of ions, there will not be any conduction of electricity right now. So due to that reason they are not conducting electricity in their solid state. But when you place this ionic compound in aqueous medium, what happens when you place ionic compound in aqueous medium, they are getting dissociated as Na plus and Cl minus. So now these free ions move here and there and they are now ready to conduct the electricity. So now NaCl, like ionic compounds in their aqueous state, in their aqueous medium, in their aqueous forms as well as in their molten state. It means molten means that compound, ionic compound will be in the liquid state. Okay, in that aqueous form and in the molten form ionic compounds conducts electricity. Okay, so in the molten state or in the aqueous solution they are good conductors of electricity because ions are free to move. So what is the reason? Because ions are very free to move here and there, so that makes the reason for electrical conduction in the aqueous medium as well as in their molten state, but it will not be a conductor in their solid state. Okay, in the solid state it is not a conductor. Okay, that's it. You remember these points again. Okay, then next, explain the hybridization involved in PCl5. What is the hybridization of PCl5 molecule, they are asking. Again very easy. Yes guys, you can expect one question directly from this hybridization concept. Okay, either in 8 marks or in 4 marks you can get a question in IPE exam for sure, that is for sure. Okay, right. So look at here what they are saying. So PCl5 will be having sp3d hybridization. What is the hybridization? sp3d. I will tell you how it is sp3d and all. See, phosphorus is there, around how many chlorines are there here? 5 chlorines are there. It means each chlorine atom will make a bond with phosphorus by using 1 electron from phosphorus and 1 electron from chlorine. Like a covalent bond is formed by mutual sharing of electrons now. So, 1 electron comes from phosphorus and other electron comes from chlorine. So, like that they will make a bond. Like that, how many unpaired electrons should be there with the phosphorus? 5 unpaired electrons are there now, because there are 5 chlorine atoms. So, 5 unpaired electrons are there because chlorine is monovalent atom, it can form one bond, like odd number of bonds. So, it means each chlorine makes one bond with this phosphorus, so that 5 unpaired electrons should be present in the phosphorus right now. So, now how do we get that 5 electrons? Just listen to these words, I mean I will explain everything clearly. See, first of all, phosphorus atomic number is how much? It is 15. So, nitrogen family, right? So, 15. So, how do you write this? After writing neon, that is 10 over, 10 electrons are over, then you can write 3s2 3p3. What is the electronic configuration? Valency electronic configuration 3s2 3p3. So, after this we have 3d orbital, but it is an empty d orbital. So, 3d0 I am writing. Now, if you represent them in their orbitals, how do you represent? So, here in 3s 2 electrons, in 3p 3 electrons. Okay, 1 2 3 like this. So, after this 3d orbital is there which is empty. Can represent that 3d orbital also like this. 5d orbitals will be there. Okay. Now, if you observe how many unpaired electrons are there? 1 2 3 only, but how many we required? 5 required now. So, that's why these orbitals will undergo hybridization. What do we mean by hybridization? They will redistribute. See, I am writing 3s separately, 3p separately, 3d separately right now. So, why we are making them separately? Because they have different energy levels. Now, what happens? That all orbitals will mix. So, when they are intermixing, what happens? They will redistribute their energy with equal amounts to everyone. Okay. So, now what happened? These orbitals, see, when one s orbital, 3 p orbitals and 1 d orbital of phosphorus are mixed, they form 5 sp3d hybrid orbitals, because we required 5 unpaired electrons now. So, now what is happening? 1 electron from here getting excited here. So, how do you write? So, you will be writing like this. So, 1 2 3 4. So, 1 2 3 4 5. This is d orbital. So, along with this we have this empty orbitals also beside this. So, now what is happening here? We have 5 electrons now, fill 1 here, the next one here, 2 3 4 5. So, like this 5 electrons are paired up. Okay. So, now after making in this way, so now what happens, tell me? So, what are the orbitals involved in the equal energy sharing? S1, P3s and D1. So, you can say sp3d hybridization. What is a hybridization? sp3d hybridization. Just to represent these empty orbitals here, whatever the vacant orbitals are there, they just represent here. Okay, right. Now, what is happening here? So, with each one unpaired electron, one chlorine will be get paired up like this. Okay, because chlorines are having one unpaired electron now. Yes, like this you will get the molecule hybridized. So, now what is the hybridization of molecule? sp3d. So, how many orbitals are there? 1 s, 3 p's, 1 d. So, total 5 now. So, 5 hybrid orbitals are present. Why I am using the word hybrid? So, when I say hybrid orbital, all of those orbitals will be having equivalent energies. You should not call it as s orbital, you should call it as sp3d orbital. Like that, how many are there? 5. Okay, right, right. So, now see, the ground state electronic configuration will be like this. Okay, like this, that is what we have written there. Okay, after that what happens? First excited state electron, what happens? One of this 3s electron is shifted here. So, that is what? 3s2, 3s1, 3p3, 3d1, that is what we have written. Now, p orbital has 5 unpaired electrons which undergo sp3d hybridization. Each sp3 hybrid orbitals overlap with a 3p orbital of chlorine. Like that, it will form 5 phosphorus chlorine sigma bonds. Okay, therefore, it will be resulting into this kind of geometry. So, what is that? So, here you have at the center you have phosphorus. Okay, how many orbitals are there? So, there are 5 orbitals now. So, you can just place 3 orbitals in the plane like this. Okay, after placing that 3, so in the plane you are placing 3 orbitals like at 120 degrees to each other. Okay, and one orbital goes upside, other one orbital goes downside, like here one orbital, here one hybrid orbital. Okay, so this is about the scenario of PCl5 phosphorus. Okay, now chlorines are there now. How many are there? So 5 chlorines, each chlorine 1 electron and phosphorus 1 electron will get paired up like this. Okay, so 3p orbital of chlorine will be involving from chlorine side, from side atom. Like that, what we got? sp3 hybridization, sp3d hybridization. So this geometry, this arrangement of atoms around the phosphorus is called trigonal bipyramidal. So why we are calling it as trigonal bipyramidal? See, we will get, first of all we will get something like this. Okay, first of all we will get a geometry like this, 3 chlorines in the plane. Okay, like this. Now one will come above the plane and one will be below the plane like this. Okay, so you got a trigonal with, if I join all these things, what happens? A pyramid is formed above side and one more pyramid below side. So trigonal bipyramidal middle geometry. What is that? Trigonal bipyramidal. In the short form you can say TBP geometry for this molecule. Okay, so this is how you need to write the structure and their hybridization. Okay, is this clear, guys, those who are in the live session? Right. So this is what we have drawn there. So now what is the angles we have discussed? So in these 3 trigonal bipyramidal geometry, in the trigonal bipyramidal geometry, in those are in the plane, that is trigonal planar one will be having 120 degrees with each other. Okay, so this one, so there are 3 120 degrees angles. Okay, now one which is above the plane, below the plane, now that will be having 90 degrees angle. Okay, so like this, 90 below with 90, above also with 90. Okay, that's it. Okay, right. So you can see here there are 3 bonds lies in the plane. So these 3 bonds lies in the plane. Now these 3, those should be called as equatorial. So equatorial bonds are with what angle to each other? They are with 120 degrees angle to each other. Okay, and there are 2 bonds above the plane and below the plane which are called as axial bonds. What is that called? Axial bonds having 90 degrees to the plane. How do they arrange? They are arranged 90 degrees with respect to this plane right now. So 90 degrees with the plane. Thus PCl5 has a trigonal bipyramidal shape. What it has? Trigonal bipyramidal shape. What are the bond angles you are seeing? 120 and 90. That's it, 120 and 90. Okay, right. Next one is explain the hybridization involved in SF6 molecule. What is that? They are asking hybridization involved in SF6 molecule. Again it is very easy, similar to the above discussion. Here sulfur belongs to 16th group element, so it has 6 valency electrons. Okay, 6 valency electrons in the sulfur, and how many fluorines are there? 6 fluorines are there. So for each fluorine there will be 1 electron, 1 unpaired electron is present in each fluorine. So it means 1 more electron is required for fluorine to fulfill its octet right now. So that's why the 2p orbital of fluorine will combine or with overlap with the orbitals of this sulfur. Okay, so now what is the hybridization required for this sulfur? Since fluorine is monovalent, it required 6 unpaired electrons to make 1 bond with each of the fluorine with the sulfur right now. So that it required 6 unpaired electrons from the sulfur. So there are 6 hybrid orbitals are required from this sulfur right now. So now look at here. So 1 s orbital and 3 p orbitals and 2 d orbitals of sulfur will mix and they will form 6 sp3d2 hybrid orbitals. How many are forming? sp3d2 hybrid orbitals. 1 s, 3 p's and then next 2 d's. So total is how much? 1 plus 3 plus 2, 6 now. So that is what they are saying. Okay, I will explain you very clearly. Just listen to me here what I am discussing. See, sulfur, what is the atomic number? I told you 16. How do you write its electronic configuration? Here neon 10 over, then next 3s2 3p4, like this we can write, and the next 3d 0. Okay, so now how many unpaired electrons are required? 6 are required, but how many we have? Just check here. 3s will be 2 electrons, in the atomic orbitals, and P will be having 4 electrons, like 2 unpaired electrons here, and 2 are paired. Okay, the next D will be 5 empty d orbitals, like this. Now what we know, we require 6 unpaired electrons to make 1-1 bond with each of the fluorine right now. So for that purpose, so this molecule will undergo excitation. After second excitation, this electron will get excited here, after that this electron will get excited here. Therefore you are going to get a hybridization of this kind. So just listen here what I am writing. So one s and p's, the next out of these d orbitals, so here 1 electron, second, third, fourth, and this is shifted here now, fifth, and this is shifted here, sixth. Now these are the orbitals involved in the hybridization. So how many orbitals and what are the orbitals? S, p3s, d2s. So what is the hybridization of the molecule? Now you will get sp3 d2. So now each fluorine will combine with overlap with each of this unpaired electron present in sp3d2 hybrid orbitals, like this. Okay, right. So is this clear? Is this clear or not? Yes, I hope this is clear. So now look at this, how many excitations required? 2 excitations required. Okay, right. So now sulfur has 6 unpaired electrons, each will undergo sp3d2 hybridization here as we discussed. Now each sp3d2 hybrid orbitals overlap with the 2p orbital of these fluorines. Okay, forms 6 sf sigma bonds. How many sigma bonds? This is sulfur, this is fluorine. 1 sigma, second, third, fourth, fifth, sixth. So like 6 sigma bonds are resulting. Okay, and after this, how the structure will be looking here? So the octahedral structure. So for sp3d2 geometry, you are sp3d2 hybridization, you are going to get a geometry of octahedral. What is that? Octahedral. Okay, so how this is looks? So at the center you write sulfur, like this 4 fluorines are mentioned here, fluorine, fluorine, fluorine. So how it is looking? Like a square now. If you join all these things, you will get like a square. So on this square you place one more fluorine, because SF6 now, here you have written only 4. So you can write 1 fluorine above side and 1 fluorine below side. Like this you are going to get a square with 1 fluorine above and 1 fluorine below. Okay, so this kind of geometry is called octahedral geometry. Okay, so now how they are oriented? 90 degrees to each other. How do they oriented? 90 degrees to each other. Okay, and if you take opposite sides, so it means between this one and this one, it will be 180. So there are 90 and 180 degree angles are present here. Okay, you just write 90 and 180 degrees angles. What is the bond angle? So between 2 fluorine atoms here, if you compare, that is 90. Okay, but if you compare with the opposite fluorine which is present above and below, which is exactly opposite, that will be 180 degrees right now. So you can write 90s and 180 degrees angles are present in the molecule in the sp3d2 hybridization. Okay, right, in octahedral geometry. That's it. Okay, so this is what I am saying here. 9 bond angles are 90 and 120. You can call it as octahedral. Okay, what is that? Octahedral you should be calling. So all 6 bonds are symmetrically arranged around the sulfur. Yes, all 6 are oriented 90 degrees to each other. They are symmetric around the sulfur. Okay, right. This is about hybridization in SF6 molecule. The next thing you need to know is one more question, that is hydrogen bonding. One of the important question. Hydrogen bonding. What is hydrogen bond? And explain different types of hydrogen bonds with an example. Very easy. I will explain you. Just listen to me. See, hydrogen bond is nothing but an electrostatic force of attraction. So now how this electrostatic force of attraction is possible? See, whenever there is an atom which is more electronegative, what I am saying, a more electronegative atom is there, to that hydrogen atom must be connected. What I am saying, a hydrogen atom is attached to more electronegative atoms like fluorine, oxygen, nitrogen, like that. Okay, so hydrogen atom attached to the fluorine here, more electronegative atom. Now what happens? The electrostatic, I mean there is polarity in this bond will be taking place. Now partial negative charge on the fluorine, partial negative charge on the fluorine, and partial positive charge on the hydrogen. Why these poles are generating? Because there is large electronegative difference between the two atoms now, so that's why it is getting partial positive, partial negative charge on the fluorine. This is clear now. And after this, now what happens, like this you take one more HF molecule, if you take, now this one more fluorine will be negative on this molecule and here it will be positive, right. Now what happens between this electronegative fluorine atom and this hydrogen having opposite poles now, so between these two opposite poles there will be electrostatic force of attraction. So the electrostatic force of attraction is the electrostatic force of attraction between hydrogen atom that is attached to more electronegative atom and the adjacent more electronegative atom will be considered as hydrogen bond. What is this called? Hydrogen bond. Okay, what is the minimum criteria here? There should be electronegative atom and a hydrogen atom should be there that must be attached to electronegative atom. Now the electrostatic force of attraction between this electronegative atom and that hydrogen atom is called as hydrogen bond. That's it. Okay, so this is how you need to represent. Now if you consider a water molecule that we are much familiar, see, water will exist in liquid state just because of hydrogen bonding. What is the reason? Hydrogen bonding. How it will be? Just see here, you take water molecule here, so just H2O I am writing like this is one H2O molecule and this is another H2O molecule. So if you take a glass of water, there will be large number of water molecules now, so between the water molecules there will be intermolecular hydrogen bonding. What we have? Intermolecular hydrogen bonding. How that will be forming? See, oxygen is more electronegative atom when we compare with these hydrogens, so oxygen will get partial negative charge and hydrogen will get partial positive charge. Okay, similarly the adjacent molecule also, oxygen will get a negative charge, hydrogen will get a partial positive charge, like this right now. So now what happens between this negative charge and this positive charge poles? There will be interactions now. Those interactions are called hydrogen bonding. Okay, between this partially negative oxygen and this hydrogen, these interactions are there now, so we can call them as hydrogen bonding. So due to this hydrogen bonding, water is existing in liquid state. Now what type of hydrogen bonding it is? See, this is one molecule, this is one more molecule, two adjacent molecules, two different molecules, like this is one and this is another. So between them it is taking. So between two molecules, between the molecules, if it is hydrogen bond, then that should be called as intermolecular hydrogen bonding. What you can call? Intermolecular hydrogen bonding. And one more type of hydrogen bonding is intramolecular hydrogen bonding. It means intra, it means within the molecule itself hydrogen bonding will be taking place. It means here you just see, here I am writing OH group and here I am writing nitro group. Like this. Now what happens, this oxygen is more electronegative than this nitrogen, therefore oxygen get partial negative charge, nitrogen partial positive, and here hydrogen partial positive, because this bond also get polarizes towards oxygen now, so negative. So between this hydrogen of this OH group and oxygen of this nitro group will get this kind of attractions, that electrostatic force of attraction. So this is nothing but electronegative atom is there here and hydrogen atom attached to electronegative atom. So there is electrostatic force of attraction between these two oppositely charged poles right now. So this is called hydrogen bonding. But what type of hydrogen bonding? This hydrogen bonding is taking within the molecule. See, the complete atoms or complete connection is within the molecule now. So you can say it is intramolecular hydrogen bonding, whereas this is one molecule, this is the adjacent other molecule right now. So if it is between two molecules, you can say intermolecular hydrogen bonding. If this is within the molecule, intramolecular hydrogen bonding. So simply remember, for intermolecular hydrogen bonding there is minimum of two molecules required. What I am saying, intermolecular bonding will be possible, intermolecular hydrogen bonding is possible when there is a minimum of two molecules right now. If only one molecule is there, so that will be having a possibility to form intramolecular hydrogen bonding only. Okay, so this is what you need to remember here. So right, so now read this thing. A hydrogen bond is an electrostatic force of attraction between a positively charged hydrogen atom that is attached to electronegative atom like oxygen, nitrogen, fluorine, and lone pair electrons on the other electronegative atom. That's it. Okay, that is the electronegative atom adjacent. Okay, now strength. How can we compare this? The hydrogen bond is weaker than these covalent bonds but stronger than the other van der Waals forces. Okay, this is also to be remembered and you need to represent in this way with one example. Then next, what are the types we discussed? One is intermolecular, other one is intramolecular. For intermolecular, what I told you, formed between hydrogen atoms of one molecule and the electronegative atom of the other, okay, other molecule. So leads to association of molecule. So this will be the example in the water. That's why water exists in liquid state. And how many hydrogen bonds are possible for one water molecule? It is a maximum of 4 it can form. Okay, right. See, if I say H2O and H2S, both belongs to 16th group only, na, hydrates of 16th group. So water is in liquid state but hydrogen sulfide is in gaseous state. Why? Because there is no hydrogen bond here, but here hydrogen bonding is there. So that makes it to be water to be a liquid in state, whereas H2S due to absence of hydrogen bonding existing gaseous state. Okay, that's it. Is this clear? Right, right. These are some examples for intermolecular hydrogen bonding that we discussed very, very clearly, right? Everything is clear. And the next one more is intramolecular. I told you. What is the example of intramolecular? I told you that molecule should contain both donor and acceptor site within the molecule. Then we can say that is intramolecular hydrogen bonding. These are the two examples like salicylaldehyde and the next orthonitrophenol are best examples you can mention in the exam. Okay, right. Right. This intramolecular hydrogen bonding is formed within the same molecule between the hydrogen atom and a nearby electronegative atom. That provides molecular stability and sometimes reduces solubility. See, remember, due to intramolecular hydrogen bonding, stability of molecule increases when compared with the intermolecular hydrogen bonding. Okay, remember this. And second statement, the solubility due to intramolecular hydrogen bonding decreases when we compare with the intermolecular hydrogen bonding. Now they will give two examples like orthonitrophenol, paranitrophenol. So which is having more solubility, they will ask. Paranitrophenol will be having more solubility when we compare with this ortho, because in this ortho compound there is intramolecular hydrogen bonding that results to decrease in the solubility. That's it. Okay, so this is an extra point I just wanted to add so that it will be useful for your other competitive exams along with your IPE preparation. Okay, right. So everything that we discussed is clear now, right? Guys, those who are watching this live session, if our discussion is really clear and it's helping you a lot, then you can just click on the like button and you can mention your feedback in the chat box. Okay, so thanks for watching. Stay connected with us and you can share with your friends. Thank you.